There is something strange happening far beyond Neptune. Something we cannot see, but we can measure. Not a planet, a black hole, not the kind that swallows stars. Not even the remnants of a dying sun, something much smaller, roughly the size of a bowling ball, yet with the mass of 5 Earths silently orbiting our own star. It sounds impossible, but the gravitational evidence is real. And now NASA, along with multiple research teams around the world, is taking this idea seriously. This is a dwarf planet, a small icy world orbiting in a region of space far beyond Neptune. Its closest approach to the Sun is about 80 astronomical units. That's 80 times the distance between Earth and the Sun. To put that in perspective, Neptune orbits at about $30 Australian. Pluto at its closest comes in at around $29.60. So VP-113 is way out there. It's in what astronomers call the inner cloud. A region so distant and so poorly understood that we're still trying to figure out what's even out there. But the weird thing about 2012 VP-113 isn't just its distance. It's the shape of its orbit. This object follows an extremely elongated path around the Sun. At its farthest point, it swings out to about $452 Australian. At its closest, it's still $80 Australian away. That's unusual. Most objects in the solar system have more circular orbits. But what's really strange is that 2012 VP-113 isn't alone. There's another object called Sedna, discovered back in 2004. Sedna has a similarly extreme orbit. Its perihelion or closest approach to the Sun is $76 Australian. Its aphelion or farthest point is an astonishing $937 Australian. These two objects are what astronomers call cedoids. They're part of a group of extreme trans-Neptunian objects or ETNOs that orbit far beyond the influence of Neptune's gravity. And here's where it gets interesting. By 2016, astronomers had identified 6 of these ETNOs with orbits that shared something peculiar. Not only were their paths stretched out and distant, but they were also aligned with each other. Their perihelia, the points where they come closest to the Sun, were all clustered in roughly the same direction in space, and their orbital planes were tilted at similar angles. This kind of clustering shouldn't happen by chance. Over billions of years, the gravitational influence of the known planets should have randomized these orbits, scattering them in all directions. But that's not what we see. Instead, these objects are moving as if something massive and unseen is shepherding them into similar paths. Astronomers calculated the odds that this clustering was just a coincidence. The result, about 0.007%, that's roughly 1 chance in 15,000. So, either we're witnessing an extraordinarily unlikely coincidence or there's something out there that we haven't discovered yet. Something with enough gravitational influence to shape the orbits of objects billions of kilometers away from the Sun. In January 2016, 2 astronomers at the California Institute of Technology, Konstantin Batygin and Mike Brown, published a paper that offered an explanation. They proposed that a massive planet somewhere between 5 and 10 times the mass of Earth is orbiting the Sun at an extreme distance. This hypothetical world would have a highly elliptical orbit with a perihelion around 280 astronomical units and an aphelion that could stretch out to 1,120 Australian dollars or more. It would take this planet somewhere between 10,000 and 20,000 years to complete a single orbit around the Sun. If it exists, this would be the 9th planet in our solar system. A true planet, not a dwarf planet like Pluto. Something massive enough to dominate its orbital region and clear out any debris in its path. Batygin and Brown called it Planet 9. The idea wasn't entirely new. Astronomers have been speculating about undiscovered planets in the outer solar system for more than a century. But this was different. This time the evidence was stronger. The clustering of the ETNOs was statistically significant and computer simulations showed that a planet with the right mass and orbit could explain not just the clustering but several other oddities in the outer solar system. For example, Planet 9 could explain why some objects are on orbits that are nearly perpendicular to the plane of the solar system. It could explain why certain high-incarnation trans-Neptunian objects exist at all. And it could explain the orbits of objects that cross the paths of the giant planets but somehow remain stable. The hypothesis made sense. It fit the data and it gave astronomers something concrete to search for. But there was a problem. Planet 9, if it exists, would be incredibly difficult to find. At such an extreme distance, it would reflect very little sunlight. It would be faint, dim, and moving slowly across the sky. Searches were launched using some of the most powerful telescopes on Earth, including the Subaru telescope in Hawaii. Astronomers scanned the regions of the sky where Planet 9 was most likely to be, but so far nothing has turned up. By 2021, Brown and Badian had refined their predictions. They accounted for observational biases and reanalyzed the data. Their updated estimate placed Planet 9 at a distance of about $380 with a mass around 6.2 times that of Earth. Still, the planet remained elusive. Some astronomers began to question whether Planet 9 existed at all. Maybe the clustering was a result of observational bias. Maybe we were only seeing a small unrepresentative sample of objects, and if we found more, the pattern would disappear. Others proposed alternative explanations. Maybe a passing star had disturbed the orbits of these objects long ago. Maybe there was a disk of smaller bodies out there massive enough to create the clustering through their collective gravity. Or maybe some researchers suggested it wasn't a planet at all. Maybe it was a black hole. When we think of black holes, we usually think of two kinds. The first kind is the stellar mass black hole. These are formed when massive stars run out of fuel and collapse under their own gravity. They typically have masses between about 3 and 20 times that of the Sun. The second kind is the supermassive black hole. These are the giants that sit at the centers of galaxies, including our own Milky Way. They can have masses millions or even billions of times that of the Sun. But there's a third kind of black hole that's purely theoretical. We've never detected one directly, but if they exist, they could be almost anywhere. These are called primordial black holes. Primordial black holes would have formed in a very early universe, less than a second after the Big Bang. During this chaotic period, regions of space with slightly higher density than their surroundings could have collapsed directly into black holes. Unlike stellar mass black holes, primordial black holes don't have a minimum size. They could be as small as a subatomic particle or as large as thousands of solar masses. The ones that interest us today are somewhere in the middle. We're talking about black holes with masses comparable to planets. Earth mass black holes or even smaller. A black hole with 5 times the mass of Earth would have an event horizon, the point of no return, only about 5 centimeters across. That's roughly the size of a grapefruit. But despite its tiny size, it would still have the gravitational influence of 5 Earths. It would warp spacetime around it, pulling on nearby objects, just like a planet would. And here's the key point. From a distance, you couldn't tell the difference between a 5 Earth mass planet and a 5 Earth mass black hole, not just from their gravitational effects. So, when astronomers talk about Planet 9, they're really talking about a gravitational anomaly, something with mass, something pulling on those distant objects. But what if that something isn't a planet? What if it's a primordial black hole that was captured by the Sun billions of years ago? In 2019, 2 researchers, Jakob Schultz from Durham University and James Onwin from the University of Chicago published a paper exploring this possibility. Their argument was based on 2 separate lines of evidence. The first was the clustering of the extreme trans-Neptunian objects, the same evidence that led to the Planet 9 hypothesis. The second was an observation from the Optical Gravitational Lensing Experiment or OGLE, a survey that uses gravitational microlensing to detect distant objects. Over 5 years, OGLE detected 6 ultra-short microlensing events. These events lasted only 0.1 to 0.3 days, which suggested that the lensing objects, the objects bending the light, were relatively small. Based on their analysis, Schultz and Onwin estimated that these objects had masses in the range of 0.5 to 20 Earth masses. Now, there are two ways to interpret this.